looks like we're good. We're at 2% battery and it's charging, so hopefully we'll be okay. Let's go ahead and get started. Hopefully we'll have normal class time and all that. Let me just move this down. And today we're going to continue on talking about more about bonding in molecules. Kind of yesterday we talked about how single bonds and double bonds are formed using sigma bonds and pi bonds. And so we're going to continue on that track today. We're going to talk about more about p orbital electrons in unhybridized orbitals. We're going to talk about resonance. We're going to talk about molecular orbitals as well. So we're going to finish off chapter 9, and then we'll be in a good place. So let's talk about p orbitals. And let's take the case of the carbonate ion that we had yesterday, Tuesday, last week, I don't know, whenever we talked about the carbonate ion. Right, we have two formal charges on this thing. What's important to note, and I'm going to try and draw this, so we'll see. But if we want to think about what this looks like, I'm going to draw the single bonds, and I'm going to draw our p orbitals, because that carbon is sp2 hybridized, right? It has three things on it, 3 oxygens. Again, it does not matter that one of them is double bonded. 3 things on carbon means sp2, which means we have one p orbital that is left. And all of these oxygens have p orbitals. And it so happens that as I've drawn it, these p orbitals are housing the lone pairs, whereas these p orbitals are bonding. They form the double bond there. And we saw that there was really no reason we couldn't choose a different oxygen to make our double bond with, right? We saw that if we move this lone pair to make the double bond, and if we move that one back onto the oxygen, we can do the same thing. We can have our double bond be on that oxygen instead. And I'm going to draw that one down here. And again, I'm going to draw this with p orbitals only, or rather with the single bonds only, and we're going to have our p orbitals. And this time now we have the p orbital bonding between that oxygen and the carbon, and now the lone pairs are in the other 2 oxygens. And we can do the same thing on the other side, right? We can form the double bond on the left side. So let's draw the orbitals. And this time now we have our pi bond forming there, and we've got our lone pairs on the oxygens in those orbitals. So we see that kind of there's motion between these. We can move electrons from p orbitals to form double bonds and break other double bonds and form lone pairs in different p orbitals. This is the idea of resonance again. This is resonance. So we really have 6 electrons here that are moving about. Remember, a pi bond is still 2 electrons, so we really have kind of 2 electrons hanging out in all of these pi bonds. So we have 6 electrons overall, and we're able to redistribute them as we see fit. We can say, I'm going to move this lone pair to form a bond, and I'm going to move this lone pair to go into that p orbital of oxygen. We can do that. That's resonance, right? We're just rearranging double bonds and lone pairs. And so this idea then is that these 6 electrons are delocalized, which means these can move. between atoms and bonds. And so anytime we have the capability of making multiple correct Lewis structures, we're going to have resonance. And anytime we have resonance, that means we have delocalized electrons. Localized electrons, meaning they're found only in one spot. But delocalized ones can hop around. And we're going to see this is kind of best illustrated in the molecule of benzene. Benzene is, I'm sorry, I will draw this with carbons written out. Benzene is quite an extraordinary compound, terribly carcinogenic, but very interesting scientifically. So it is a ring, a 6-carbon ring, made of alternating single and double bonds between the carbons. And it turns out this thing resonates like crazy, continuously. We're going to see that these double bonds can move around. I'm using these arrows, by the way, to show how I'm moving the electrons in the resonance. This is something we do in OChem, so I'm just putting it in your heads. We're not going to really worry about the arrow pushing right now in Gen Chem, but this is how we're seeing that we're moving this bond around. So all of these carbons are sp2, all of them, right? And we can see I've resonated. I've just moved the double rounds around. And in each case, all the carbons still have octets. There's no formal charges on anything. I've just moved the double bonds around. And that's the idea of resonance. And interestingly, so a CC bond is somewhere around 1.54 angstroms, and CC is like 1.3, roughly. I might have these written down here. 1.34, actually. Interesting. But in benzene, these are all 1.4 angstroms. So they're not quite double bonds, they're not quite single bonds. They're all the same, by the way. Because of this idea of resonance, we can put the double bonds wherever we want. But we see in reality that the bonds in benzene are shorter than single bonds, but longer than double bonds. And so that has this idea of the delocalization of the electrons. We don't have discrete single bonds or discrete double bonds. We have this kind of in-between idea. And so we often will write benzene, all these vertices represent the carbons. We often write it like so, with a just giant circle in the middle. Where again, all these vertices are the carbons. We often write it with a circle inside to illustrate the delocalized nature of these electrons. And we're going to see this lends this molecule an extraordinary amount of stability. If you end up taking organic chemistry, which is all about carbon reactions of carbons, we're going to see that benzene is so stable, all the reactions we can do on normal double-bonded carbons, we cannot do on benzene because it's so stable, because of this delocalization. So it's extremely stabilized. Due to the delocalization. And we're going to see that if you take 113, you're going to see that resonance is going to be a big factor in determining how strong an acid is, how strong a base is. It's all about how well a molecule can delocalize electrons. And so we're going to see here that, that this is an important component here. So let's take a look at Google. Again, we're going to look at some better images than I can draw. We're going to look at the actual p orbitals involved in benzene and how they're able to recombine in different ways. Benzene delocalized electrons. Yeah, let's go there. Okay, so let's take a look. Let's pop over. So let's take a look at the delocalization of benzene's electrons. And let's see if we can't find some nice... These are kind of still not the best. This one. This is what I'm looking for. So we might think of... Actually, I think this is even from our book. So we might think of these as localized when we draw them as double bonds in benzene, right? Where we can say, I'm going to make the double bond here and here and here. So as long as we have the alternating double bonds, we're good. But we know they rapidly interchange. And as a result, the real picture looks something more like this, where we have them delocalized, spread out through the entire system. So we have 6 electrons here. Each pi bond is 2 electrons, so 3 pi bonds, 6 electrons, are completely shared throughout the molecule. And so this is a 6 pi electron system that's completely delocalized. And so we can see this also with other systems. Let's say, let's look at nitrate. Here we go. We might draw nitrate with a double bond and have the oxygens with their lone pairs there. Or they can be shared throughout the whole thing, which is what resonance shows us. So we really have all 3 contributing to the overall structure. Even though we might draw one of them with a double bond just because that's the way we typically do things to show octets. But in reality, we have this delocalization happening. And so this is a good reason that nitrate is very stable as compared with other compounds. So we'll see the reasons for this in other courses. But suffice it to say that we can classify things as localized or delocalized. And that's the idea here. So another example. I'm going to just draw this. I'm drawing these molecules in ways that just kills me. Okay, there we go. So another organic molecule here. And we might describe, as we have a special term for it, we call these double bonds conjugated. We have alternating single and double bonds in a carbon chain. And so we're going to see that conjugated systems will also be especially stable because they can delocalize their electrons. So we're going to see that this is something that we'll talk about in organic chemistry if you end up taking that. We'll look at conjugated systems and how stable they are due to these alternating double and single bonds, and the fact that they can resonate in between. We can say, well, I'm going to resonate somewhere else, and suffice it to say these are allowed to resonate. Since they're able to resonate, they're extra stable. And so we see that they do different things than non-conjugated systems would do. And so that's something we'll learn later on as well. So anytime you have resonance, resonance can be something as simple as having formal charges and double bonds on the same atom, like sulfate. We can resonate this. So we can go ahead and move electrons around in sulfate. We could do the same thing in this molecule. It would not be a very good thing, but we can go ahead and resonate this one as well. So there's different ways to arrange this structure. So suffice it to say, resonance causes things to be very stable. And we're going to see ramifications of that later on. But suffice to say, that's also why 3 of our strong acids that we're going to learn next semester are strong acids, because of resonance. All right, so anytime we can kind of delocalize electrons, the same thing here, delocalized pi electrons. This doesn't happen with sigma electrons, by the way, because those are always going to be localized because they're forming that single bond. It's only the pi ones that are able to move about because they're not as strong. So they're able to delocalize, but we don't see that with sigma bonds. All right, so it's also the reason that we're like able to see all this stuff from conjugation and double bonds. It's all very biologically relevant as well. So we're going to see that you can't rotate a molecule along a double bond because you'll break it. Double bonds, as we saw, those pi orbitals have to overlap. So if you try and rotate it, there's no overlap anymore. Here they're overlapping, overlap happily. If you rotate, no more overlap, no more bond. So you can't rotate a double bond, but when you break a pi bond, say by zapping it with light, you can cause it to break, and therefore you can start rotating your molecule, and that's how we see. So our eyes absorb light, which breaks double bonds and allows things to rotate, and our neurons are able to detect when that's happening, and so we can process signals accordingly. It's pretty cool stuff. You can read a blurb about it, about rhodopsin. You can read about cis and trans rhodopsin, so you can go ahead and look it up. So it's a good, it's a very important molecule. You know what, let's just do it now. Why not? Let's just look at rhodopsin and see what happens when things happen here. Okay. Oh, so much biology. All right, forget it. This is too biological. Aha, here we go. Never mind. So with the rhodopsin, it's a protein that is able to kind of detect this sort of thing. You have these molecules which are stuck in certain positions. And suffice it to say, when you zap them with light, this bond right here, number 11, breaks and reforms after the molecule rotates. And you can see a difference in shape, right? You have this kind of kink shape versus the all straight shape. And so that interacts with your proteins, rhodopsin and opsin, differently. In this case, we're looking at opsin. But suffice it to say, these retinals interact these things together. So when this happens, you have a change in the shape, and then your protein changes shape, and your brain is able to say, aha, I've detected the change in shape. We've seen light. And so it's pretty cool stuff. So just because the double bonds can't rotate, as soon as you break the double bond and allow it to rotate, then you have a change in shape. Change in shape can be detected, and so you get interesting, good stuff there. So, I guess that was retinal. Rhodopsin is part of the protein. So, let's talk about molecular orbitals now. How do molecules bond in just how do we take atomic orbitals into molecular orbitals. Let's see how things are being shared in molecular orbitals. So we know atomic orbitals. We have done this many times, yes. For example, we have hydrogen. It's got its 1s electron, right? Let's see what these orbitals look like when we have two atoms coming together, rather than just a single atom. A single atom is an atomic orbital, but having multiple atoms would be a molecular orbital. And so we're going to see that when we take two hydrogen atoms, when these two orbitals come together, we're going to see that there are two, I'm going to say this is again our energy axis here. We're going to see there's two ways they can come together. One way is of lower energy, and one way is of higher energy. And we're going to see, of course, that everything wants to be low energy. That's the main tenet of chemistry. Things want to be as low energy as possible. We're going to say that when these two atomic orbitals come together, they form molecular orbitals. So these are atomic, these are molecular in the middle. And notice that we had two atomic orbitals, and we're going to end up with two molecular orbitals. But these are going to be slightly different names. We're not going to just have 1s, because 1s talks about is an atomic orbital. But molecular orbitals have different names. We're going to see that this is the sigma 1s, and this will be sigma star 1s. And we're going to see, because we have two electrons here, those two electrons will end up populating the sigma 1s orbital. And we're going to see that that's going to form the sigma bond. We know that forming bonds always releases energy, right? It's always an exothermic process to make a bond. And so we're going to see that by putting these electrons into lower energy molecular orbitals, that's where that energy loss is coming from. So it's by making a bond, they're able to lower their energy, and we describe that using molecular orbitals. We can describe these as a bonding orbital and an anti-bonding orbital. Anti-bonding orbitals are higher energy, and therefore they're destabilizing. And we're going to see that bonding orbitals are going to be low energy, and they're going to be stabilizing. Remember, low energy equals stable, relatively speaking. So everything wants to be low energy. And so they do that by forming bonding orbitals. We see that some molecules simply will not form because there's too much anti-bonding happening, and they would just destroy themselves. We'll take a look at that later. While I've done a kind of bad job of it, suffice it to say that the delta energy here should be the same as the delta energy here. Ideally. So you would end up making one molecular orbital that is lower in energy, and your second molecular orbital, which is the anti-bonding one, is going to be equally high in energy. So whatever energy loss, any exothermic bit, whatever that change in energy was to go to the more stable orbital, you have the equal amount of energy going to the anti-bonding orbital. So, but it's then endothermic to go that way. And so we're going to see, for example, why H2 exists. because we are able to put both electrons into the sigma 1s bonding orbital. So we end up having that happen, and that's a good thing. If we try to make helium 2 plus, not helium 2 plus, let's try to make helium 2. We know noble gases don't bond, but let's take a look at that. Let's take a look at why. If we look at a helium atom, oops, heliums have 1s2, right, as their electron configuration. And if we try to make molecular orbitals with them, here we'll have the sigma star 1s, sigma 1s. One box holds 2 electrons, right? Just like we've seen before. So we're going to have 2 electrons go here, and 2 electrons go here. So this molecule is probably not going to exist. We have something called the bond order, which is the number of, let's just say filled, do I want to say filled? Let's say the number of electrons in bonding orbitals. Okay, now let me write this again. So number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals over 2. And this tells us, by the way, a bond order of 1 is a single bond. Bond order of 2 is a double bond. Bonder order, let's try that again. And a bond order of 3 is a triple bond. And we also see non-integer bond orders sometimes. But if we take a look at the bond order here of our helium, we have 2 bonding electrons. We have 2 anti-bonding electrons. So we have a bond order of 0, which tells us that no bond is going to be formed. We have a bond order that is 0, no bond. No bond is formed here. And so we're going to see here that He2 would not exist. We do not have this molecule. So it is unlikely to exist. Unlikely to exist. He does not exist. So because of the fact of the antibonding orbital, there's no energetic reason for the heliums to come together like this. And so it is not stabilizing, so they're not going to do it. In chemistry, things only happen if they make things more stable or if there's enough energy to get them to happen. So this is not going to happen. There's no energetic reason for it. It's not thermodynamically favorable. Not going to happen. All right? Cool. Let's take a look at another one. How about... Let me make one more note here before we move on. Suffice it to say, when you're comparing things, a higher bond order is something that's more stable when you're comparing things. And we're talking about similar things. So no apples and oranges here. We're talking like Golden Delicious and Granny Smith. Those we can compare, right? Different types of those. And by that, I mean, let's take a look at something like this. Let's see, we've seen He2. What about He2 if we had a positive charge on it? Positive charge, remember, means we're lacking an electron. We have one fewer electron than we would normally. So let's take a look at that. And it doesn't really matter which one you get rid of. I'm getting rid of the one on the right. One of the ones on the right doesn't matter. Because we're going to see now, when we make our molecular orbitals, we're going to see we end up with the following. We put 2 electrons into 1s. We always fill from bottom to top, low energy to high energy. We have 3 electrons total. So we're going to fill 2 into the bottom bonding orbital, and we're going to fill 1 into the anti-bonding orbital. If we do the bond order of this, be 2 bonding electrons minus 1 anti-bonding, divided by 2 is 1/2. We saw that the bond order for He2 was 0. The bond order for this one is 1/2. 1/2 is greater than 0. So we would say that this species would be more stable. Because it has a higher bond order. So it's more likely to happen, although again, this is unlikely. We don't typically see this. This is all theoretical stuff right here. Well, some of this. And so we can throw all these fun random molecules that may or may not exist, or ions of them, and we can see what those look like. And so there's a lot of interesting things we can do with these. All right, so let's go ahead, and so the idea here is that we're able to justify that this He2 plus thing would be more stable than He2 itself because it has a higher bond order. Again, this is something that we're comparing because they're both helium atoms in both molecules. These are very similar to each other. The only thing is we've taken away an electron. Therefore, we're able to compare them. We're not going to be able to say, well, He2 plus versus H2, like, they're not the same elements involved, so you can't really compare them. So just understand that. We can compare them if they're similar enough. And usually that means we're just changing the charge. All right, so let's take a look at, let's go on in our periodic table here. Let's look at lithium. Let's look at dilithium. For your Star Trek friends. It's their fuel source, right? Dilithium. Lithium has multiple things here. So we're going to see that we're going to do molecular orbitals for the 1s. And I foolishly did not leave enough space. But suffice it to say, the molecular orbitals for the 2s are also the same idea. We still split them. So this is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. We're going to see that, of course, these bottom ones will be filled. So we have nothing participating there. And then we have the 2s electrons forming a bond in the sigma 2 orbital. So if we look at the bond order here, and I'll actually write it out this time. Bond order. Bonding minus antibonding. So we have 4 bonding electrons, 2 of them in sigma 1s, 2 of them in sigma 2s, so 4 altogether, minus 2 that are in sigma star 1s, divided by 2 equals 1. So we would expect that lithium could form a single bond with itself. So we have this as a potential option. However, while this is a theoretically possible molecule, it is unlikely simply because lithium is just more likely to just lose the electron rather than try and make covalent bonds. It could make those double bonds, but it's unlikely. We would describe the orbitals for this, by the way. Remember how we talked about talking about atomic orbitals 1s2, 2s2, 2p6, all that fun stuff? We can do the same thing for molecules. So lithium 2, we would say it's sigma 1s2, sigma star 1s2, sigma 2s2. That would be the configuration for this. So we can do that as well for this. So fun, fun, fun. We can keep doing electron configurations, but now for molecules instead. So we would say, well, this thing appears to exist. So that's pretty cool. So the Li2 molecule would be stable if it were to form. Again, unlikely just because the lithium atoms are more likely to just lose their electron. But again, theoretical stuff here. All right, just for the future, because we're going to talk about more of these, I'm going to just omit the bottom half of all these. We're going to see everything in period 2 will have sigma 1s2 sigma, not q, sigma 1s star 2. Everything will have those two filled, right? So their 1s electrons are core electrons. They're not going to really be participating in bonding. So we're just going to forget about them. So we're going to ignore the 1s electrons. And then we're going to see that everything from, I'm getting ahead of myself. Well, we'll look at some more. Let's look at Be2. Actually, it's not. It'll be the same as helium. It's not going to exist. Boron 2 is going to be more interesting. Let's see what happens when p orbitals come into play. When p orbitals come in the scene, we're going to see that we can form, again, bonding or anti-bonding things. If you really want to see the physics behind it, it's all about wave interference. So electrons have waves. They behave as waves. When waves interact, they can either add on to each other or they can cancel each other out. And we see that that happens with the anti-bonding orbitals, is their waves cancel each other out, and so nothing can exist there. We'll take a moment to look at interference patterns, just so we can see this. So notice here, if we have two waves that are completely in sync with each other, if we add them together, we get this big wave up top. If we have waves that are completely out of sync with each other and we add them up, we get a flat line. We get nothing. And so we can see this is called interference. And we're going to see when we have anti-bonding orbitals form. So if we have s orbitals coming together, they can make anti-bonding orbitals if their waves happen to interact poorly. If we have the wrong phases interacting together, that's where we get these anti-bonding orbitals, where there's in fact this area in between them that no electrons can exist. And if they can't share their electrons, they're not going to form a bond. And so we're going to see that that's the case. When they do form a bond, it's because they're able to constructively interfere. They add together. Their waves add together. But when they destructively interfere, we end up getting nodes in between them that we can't cross. And we're going to see the same thing for pi. When our phases are aligned, we get nice pi bonding. When they are out of alignment, when they're out of phase, they destructively interfere. And as a result, we get anti-bonding happening between them. Okay, so that's the idea here. So if we kind of imagine the waves, there is going to be an area when we add them together that's going to cancel their equations out. And if you cancel them out, they don't exist there, and so you get anti-bonding. That's destructive interference. Suffice it to say that it's just all about how they're overlapping. If they're overlapping constructively, bonding. If they're overlapping out of phase, destructively, there's anti-bonding. So let's see what happens when p orbitals enter the scene. We're going to see that when p orbitals come in, we're going to have multiple things happening. Let's take a look at boron. Boron has 2s2p. I'm going to ignore the 1s stuff because remember everything in period 2 has sigma 1s2, sigma star 1s2. Everything's going to be the same, so we can just ignore it. They just cancel each other out anyway, so we're not going to worry about that. Boron has 3 electrons in 2s and 2p altogether. When we actually put these together, I again should have separated them more. Bring them closer and closer together, but suffice it to say there is a sizable energy gap here. So we get sigma 2s, sigma star 2s, just like before. And we're going to see that after beryllium, we don't even care about the 2s orbitals anymore because they're just going to be completely filled. We have 2 electrons and 2s for each atom. So we're going to have 4 electrons in the molecular orbitals for 2s. So they're going to, again, cancel each other out. With p orbitals, we have interesting things happening. We have, we're going to end up splitting this into 6 boxes. We're going to have pi 2p, sigma 2p, pi star 2p, and sigma star 2p. And this is going to be the same pattern for boron, carbon, and nitrogen. They all have patterns that look like this for their 2p orbitals. So all of these technically are connected, and I'm trying to draw them good, but I'm not very good at drawing, so suffice it to say this sigma 2p and pi 2p are both lower energy than 2p, even though I haven't really drawn it that way. We're going to see that these are going to be the bonding ones. And these are anti-bonding. And so if we are going to fill the 2p orbital, pi 2p, we're going to fill it just like we did with our atomic orbitals, 1 electron at a time into each box before we start pairing off. So we're going to put them like so. We're going to end up having our boron, our diboron, I guess, with having two electrons in pi 2p, but they're going to be separate from each other. And that's going to be important for the properties of it. So we might describe this electron configuration. Of course, we have our 1s orbitals. I'm okay if we just say we can't really use a cheat on this. Then we have 2s, sigma star 2s, and then pi 2p. And again, even though they're two different pi orbitals, they are degenerate equal energy, so we just lump them together in our configuration. This is B2, diboron. And the important part is here we have unpaired electrons. Unpaired electrons in molecular orbitals lead to something called paramagnetism. We're going to see that B2 diboron will be paramagnetic, which means it is going to be affected by magnetic fields. And it's interesting. So we're going to see that it's going to be actually weakly attracted to magnetic fields. I'm going to just say that. I'll just say that besides affected, weakly attracted to magnetic fields. Whereas we're going to see that things that have completely paired electrons will be diamagnetic, which are weakly repelled by magnetic fields. And so we're going to see that that's the case. We can classify molecules as being paramagnetic or diamagnetic, depending on how their electrons are paired. And so we see here we have the pi 2p orbital. That one has two unpaired electrons in it, and as a result, the molecule is paramagnetic. And we're going to see here that our next one, carbon, would not be paramagnetic. Bond order for this, of course, would just be 1. The sigmas all cancel out, so we just have 2 pi bonding electrons. All the antibondings cancel out with previous bonding, so we're good. So just again, for the next part, I'm going to ignore for everything between diboron and dineon. So we're going to not focus on the 2s anymore. We're only going to look at the 2p's. Because, again, these cancel each other out. 2s and 2s star cancel each other out, so we don't really need to worry about them. We're going to get the same bond orders whether or not we include them, because those two will cancel each other out. So core electrons don't really, well, they're not core electrons, but they're lower energy. They're not going to be participating in the bonding. So let's keep going. How about we look at N2? N2, we have the same idea. Again, I'm just looking at the p orbitals now. Nitrogen has 3 p electrons. And I'm again omitting 2s. So we're going to have the same construction as before. We have pi 2p, sigma 2p, pi star, sigma star. all these theoretically connect. Okay, so if we're going to fill this out, 1, 2, 3, 4, 5, 6, we're going to see that the bond order of N2 would be 6 minus 0 over 2, which is 3, which tells us triple bond. And if we consider the Lewis structure of nitrogen, we see indeed our Lewis structure also predicts a triple bond. So this is confirmatory evidence that we have a sigma bond there, and we also have 2 pi bonds that are taking place here. So we're going to have a triple bond be here. So actually that sigma 2p are the non-bonding ones, but we're not going to worry about those. So we expect a triple bond from the bond order here. That's the idea. Okay, so we end up making a triple bond in our molecule. That's what we would expect this to be. All right. If we're to compare, say, N2 minus, N2 plus, and N2, we can compare them by looking at their molecular orbitals. Let's compare these. N2 minus, N2 plus, and N2. Let's see what's going to be, what our stabilities are going to expect to be. So, let's take a look. So N2 we just did. We have a bond order of 3. Let's look at N2 minus. So I'm going to give one of them a 4th electron because we have a minus charge. Pi 2p, sigma 2p, pi star 2p, and sigma star 2p. And by the way, we would expect nitrogen to be diamagnetic, right? It's fully paired off in its molecular orbitals. The things in the middle, those are fully paired off. This is a diamagnetic species. So it's just a good practice because, just do it every time you're doing one of these. Just see, is this thing going to be paramagnetic or diamagnetic? So let's fill them out. 1, 2, 3, 4, 5, 6, 7. So this is paramagnetic. We have an unpaired electron. The bond order is going to be 6 minus 1 over 2, which is 2.5. So we're expecting this to be less stable than N2 would be. And if we go ahead and look at N2 plus, I really need to just copy paste these things, don't I? I'm going to take away one of the electrons from one of the nitrogens. All right, let's go ahead. Here's our boxes again. Pi 2p, sigma 2p, pi star 2p, sigma star 2p. 1, 2, 3, 4, 5. So this would also be paramagnetic. If it is, you can go ahead and look at its what am I saying? Bond order. Also 2.5. So we would say that N2 is the most stable And N2 minus and N2 plus would probably be equally less stable. So we would say that N2 is better than N2 plus, which is about equal to N2 minus in terms of their bond order. So we can make these comparisons. We can see what's going to be more stable, what's going to be less stable. All right. Questions on this stuff so far? Usually by now there's like a ton of questions. We've got like 50 of you here. Okay. We'll keep going. If we look at the ones from oxygen and beyond, we see we have one thing switch here. Let's take a look at it. If we look at oxygen, dioxygen, oxygen has 4 electrons in the 2p orbitals. Again, I'm omitting 2s because we don't need to show that right now because we know it's going to cancel out. There's something different that happens between O2, the molecular orbitals between oxygen and neon. We're going to see that we actually have sigma 2p, then pi, then pi star, and then sigma star. So we see here that we have a switching of the pi 2p and sigma 2p. We see that sigma 2p is now lower energy than pi 2p. So between oxygen and nitrogen, that's when these things tend to change. So we're going to see that if we look at the kind of like, just accept it, I guess. That would be the easiest way to do it. So after nitrogen, so at oxygen, we switch to having the sigma now be our lowest energy, and then the pi, and then and then the other two are the same. So in this case, let's go ahead and start filling these out. And there is evidence for this, by the way. We have 8 electrons here, so 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is paramagnetic. By the way, this doesn't, paramagnetic is, it's a weak attraction, right? So when we think of magnets, we're thinking of ferromagnetism. That's a strong attraction to magnets or a strong repulsion to the opposite side of the field. Paramagnetic is a weak attraction. And so we can see what that looks like here. If we do its electron configuration, I'm going to omit sigma 1s and 2s. Sigma 2p2, pi 2p4, pi star 2p2. It's paramagnetic, and the bond order is 6 minus 2 over 2, which is 4. Which is 2. And we would expect, double bond. And lo and behold, we do have a double bond in between them. So we actually have a paramagnetic species, and we're going to see that the bond order is going to be 2, which is what we expect with the Lewis structure anyway. All right, let's take a look at Google. Let's see if we can't see what this paramagnetic stuff looks like. Let's see if we can't have a nice example. Let's see. Yes, this is what I'm going for. So, oxygen, this is an example of a paramagnetic substance. Let's see if we've got the if we've got the actual video here. Let's go back and let's look at videos instead of images. Okay, here we go. Let's see what we've got here.
It's hard to believe that Mint Mobile can be good.
Okay, so, wow, this is loud. Okay. Yeah, we don't need to see, just show us the freaking thing. Okay, here we go. All right, here we go. What is this guy even pouring? Nobody knows. We don't care. Show us the freaking magnetism. Okay. And it's not very descriptive, is it? Show us like him actually pouring it. Okay, this is a terrible video. Okay, let's find another one. Let's see what paramagnetic oxygen is. Yes. Don't. You're not going to get liquid oxygen anyway. Somehow, I hope. All right, so we're going to put it in a magnet here. Maybe. Okay. So that's nitrogen. Notice how it doesn't do anything with these magnets; it just pours right off. And so now we're going to see what happens with the oxygen. Notice how it stays there in the middle. It stays in between the magnets, unlike the nitrogen. So because of its paramagnetism, it's able to stick there. So it's pretty cool. Let's look at the nitrogen again. Nitrogen is diamagnetic. The nitrogen, we pour it on, it just splashes off. Notice how nothing stays in the middle there. So there we go. That's a much better video than that other random one. So cool. That's the idea here. So interesting stuff, yes? We see some interesting properties. All right, let's talk about ones that have multiple atoms. Let's look at carbon monoxide. We can do it with different atoms as well. We're still looking at diatomic species because putting more atoms in here just gets crazy. We're not going to worry about that. But if we look at other species, we can do it too. So carbon has got 2 electrons in the p block. Oxygen has 4. If we go ahead and take a look at their configurations, if we go ahead and start filling these up, we have 6 total electrons, right? We have 2 from carbon, 4 from oxygen. 1, 2, 3, 4, 5, 6. Bond order, therefore, 6 minus 0, 3, triple bond. We expect this will be diamagnetic as well. Everything is fully paired. Lo and behold, our Lewis structure for oxygen indeed predicts a triple bond. So we can do this with heteronuclear, multiple nuclei as well. And so you'll have a bunch of, not a bunch of, but you'll have homework problems comparing different molecular orbitals. And I better see the work on that. I better see all these lovely boxes drawn out. All right, I don't want you just saying, oh, bond order 3, right? Best be showing your work on that. This is your work. The boxes are your work. So don't think you can get away with that. And so that's kind of the idea here. So we can use these to help us predict when things are going to be stable when things are going to form, if things will not form. For example, if we have neon, let's just do neon, regular. We probably expect it's not going to form because it's two noble gases, but we can have proof. Neon has 6 electrons. I'm not going to draw that. We've got our sigma 2p, pi 2p, pi star, sigma star. And if we go ahead and fill these out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, bond order of 0, no bond. So we are going to end up seeing that dineon would not exist, right? We're expecting a bond order of 0, and so we're not going to see anything happening there. All right, so that's the idea here. So these molecular orbitals are kind of a pain in the butt sometimes. Lots of boxes. Don't forget that at oxygen, as soon as you introduce oxygen in, you're going to have the switch of sigma and pi 2p. So that pi is now the higher energy one. In boron through nitrogen, we have the opposite. We have pi 2p is our lowest energy of those molecular orbitals. So you'll have homework on this. Don't put it off. I think it's due on the weekend. And so, yeah, get to work on it. And your next exam is just going to cover these 2 chapters as well, I believe. Or if I don't remember if I include gases on it. I'll double check the syllabus, so should you. Double check the syllabus and we'll see where we are on that. And don't forget. So, good stuff. All right, so I guess that's it for today. That's the end of chapter 9 here. So chapter 10, we're going to study gases. And we're going to actually bring in some math finally. We haven't done math in a long time. I haven't been able to yell at you about sig figs for a while, so that'll be upcoming as well. So we'll start that next time. And well, you know, while I'm here, let's just check your syllabus. Let's see when what topics are on. Oh my gosh. Actually, I wonder if I have it here. C111. I do have the syllabus saved. Okay. If we look at this, this is 221, 111. There we go. Our next exam is indeed just going to be on chapters 8 and 9. So that is going to be on the 15th, so 2 weeks, and it'll just be on chapters 8 and 9. Okay, so that'll be there as well. So we'll start gases next week, and we're gonna go on from there. Gases will not be on the exam. It'll just be on this bonding stuff, and then we're gonna have gases and liquids and solids more heavily represented on the final. So that's how that's going to take place. Okay, so we have just about a month left. So keep on trucking. We're almost through it, and yeah, so great. All right, take care. I'll see you guys next time.